In this video, we'll look at sums of squares and coefficient of determination. As in the previous chapter, with simple linear regression, we start with the total sum of squares of y minus y bar squared and sum of that. See, this is when we do not include any of the x variables. We look at only the y variable and how much variability there is among the y values, and that is given by y minus y bar squared and sum that, and that is called SST, or total sum of squares. Now when we bring in all the x's and run the regression, then y hat becomes our estimate, and therefore y hat minus y bar is the amount of error that was there originally is no longer an error. Originally the error was y sub I minus y bar. Once you bring in regression, the error is y minus y hat. So y hat minus y bar is the amount of original error that is no longer present. So this is called sum of squares due to regression, and that then brings us to sum of squares of error, which is y sub I minus y hat. Now of course SSR plus SSE is equal to SST, and then once we have these sums of squares, we can put them all together in the form of an ANOVA table. So this ANOVA table for regression is almost identical to the one that we saw in the previous chapter, the simple regression, the only difference being the degrees of freedom for SSR is the number of independent variables, the number of x's, which is p, and therefore our degrees of freedom for sum of squares of error would be n minus p minus 1. The rest of the ANOVA table is same as before. So once you set up the ANOVA table, then we can find the ratio between SSR and SST. And that is our coefficient of determination. And we call this multiple coefficient determination because this is for a multiple regression. So to emphasize that this is a coefficient determination for multiple regression, we call it multiple coefficient determination, and the interpretation of R squared is same as in the previous case. The proportion of total variability explained by the regression. If you take a square root of this R squared, so we get multiple correlation coefficient. We'll look at that in the Excel sheet in a minute. But before we go to Excel, there is one more concept that we have to look at, and that is adjusted multiple coefficient determination, and that is R squared sub A. So it takes R squared and makes an adjustment to it, which is in this form. The reason for this adjustment is as you add more and more x variables into the equation, R squared will always keep going up. Therefore, if your intention is to simply maximize R squared, you can bring in all sorts of x variables, whether it is worthwhile or not, into the equation, and your R squared will keep going up and up and up. But much of the x variables that you bring in this way may add no value at all. So that's why as you add more x variables, the R squared is adjusted for the fact that the degrees of freedom for error keeps going down and down and down. So R squared sub A, the adjusted coefficient determination, is a better measure to look for when you want to add more variables to see whether R squared sub A goes up. Because R squared will always go up, so there is no point in looking at R squared. So this is a adjusted coefficient of determination. Let's look at these concepts in Excel file now. Same example as before. So R squared is SSR over SST, and we can get this value straight from the ANOVA table of the regression output. We ran the regression output in the previous video. So here is our R squared, and you see the one before that is multiple R, and that is the square root of R squared, which gives us the correlation between y and all the x's taken together. And adjusted R squared is the R squared value adjusted for the degrees of freedom. As you see, adjusted R squared will always be slightly smaller than R squared value. So we have the R squared here. Let's make that into a percentage. And the interpretation for R squared is that 90.4% of the variability in the travel times is explained by the regression. Now, adjusted R squared, of course, is from the ANOVA table again, which is right there. And here is the formula for adjusted R squared.